Hello, Thomas.
Hello.
Hello, good to see you again. Here is Monica.
Good to see you. Hello, Monica.
Oh, good afternoon, everybody. Now you will start your afternoon section. We have now Professor Thomas Gasenzer from Heidelberg University, Germany. Thank you for accepting our invitation once more. Let me present him. He did his doctorate at Heidelberg University with Professor Otto Nachmann, working on the project P-violating energy shifts and Berry phase in atoms. He had a postdoc at Chile, University of Colorado Boulder, where he worked with Moore Holland, as well as Ana Maria Ray on far from equilibrium dynamics on Fermi gases. Since 2008, he is the head of his research group at the Institute of Theoretical Physics and member of the Synthetic Quantum System Group at the Kirchhoff Institute of Physics, also in Heidelberg University. The focus of his research set is on ultra-cold atom quantum gases, and his recent research topics include ultra-cold quantum gases far from equilibrium, universal dynamics and quantum turbulence, artificial neutral networks for quantum physics, highly correlated quantum system, and entanglement. Thank you, Professor. We are now ready to start.
Right. Good. Can you hear me all? Yes?
Yes.
Good. Very good. Well, let me first of all thank you very much for inviting me to this great school. As I said, I would have really liked to come, and it was sort of sad that it showed to not work out in the end. But now I'm really lucky and happy, I want to say, that it works out in this way. And I hope you can kind of follow me here. You don't see me so closely. I could go closer, but then I can't see my slides. But in this way, you can at least sort of see me moving like I would have been standing there in front of you. So let me start straight away. The topic I announced is universal dynamics in spinor Bose gases. So I'd like to concentrate on the spinor gases, the experiments we've been doing together with Markus Oberthaler, and the theory that we've been recently doing about that. But before, let me introduce you to the topic. So universal, we're going to talk about universal, and now sit back and get calm and feel in equilibrium. Yeah. So this is as I was here feeling that almost 10 years ago, I think it was in Yellowstone, you felt like in complete equilibrium. Now, of course, we would like to not have it that warm, but we would like really to have it cold. So we're going to talk about cold gases. Because I want to talk about universality, I would like to start with an example of something really universal, but in equilibrium before we come to dynamics, because it's pretty useful to have a look at that for what I'm going to tell you later. So let's look at an equilibrium Bose-Einstein system, a thermal Bose-Einstein distribution, and just take the free ideal gas distribution you all know. Yeah? So it's written down here in the lower left. What I assume is that we're in the grand canonical ensemble such that there are two parameters. These two parameters you have to specify in order to tell what kind of state the system is in. However, you don't have to specify anything else. Whatever Bose system you take, whatever atoms it's made of or other particles, this function is merely universal. It always takes the same shape, and the only non-universal bits in there are the two parameters, in this case, the chemical potential and the temperature. Of course, you also have to specify some dispersion if you want to talk about how the excitations look like, but even at that level, it's not necessary because omega is simply the energy of the excitations. Now let's have a look at the sketch. The sketch shows you a typical Bose-Einstein distribution in a regime where the chemical potential is still negative. That is, you are in a regime above the Bose-Einstein transition temperature. It's still a normal gas, but it is already by absolute number so small that it minus mu is smaller than T. And in that case, first of all, of course, if you're going with omega, now I should actually be able to draw. If you're going with omega, the energy below that chemical potential scale, then the distribution is simply flat because omega is dominated by the chemical potential. Above, in this special case that we are with mu between the temperature scale and 0, you have this very typical Rayleigh-Jeans law, which you can simply write as the temperature divided by omega. So because I draw here a double logarithmic plot, and I will do this essentially in all plots in the following. This simple law, T divided by omega, it's a power law, is simply a straight line. So that you can see the power law by a straight line in here. So with this, you have already kind of the most essential features. We have an ultraviolet scale where the distribution is cut off here by this exponential Boltzmann. We have a power law, and then we have an infrared scale which cuts off the distribution in the infrared, below which it's essentially flat. So these three features we will now use also in the following when we go out of equilibrium. I'd just like to introduce it here in equilibrium, that you see that what I'm going to talk to you about later on is not so unfamiliar from when you think of usual equilibrium systems. Right, now let's take this distribution. We have fixed the temperature and the chemical potential, and now change it a little bit. Simply by cutting off the particles in the distribution at the highest energy. So which I have here indicated by this red volume under the curve. Let's suppose I take them away. This is equivalent to cooling the gas by means of a quench, as you typically do it in these experiments. So you open the trap a little bit, let out of the trap the hottest particles, those with the highest momenta and energies, and then you create in this way a system which is out of equilibrium, not very much, but which will, after re-equilibration, end up in a lower temperature. And this is now indicated here already by the distribution which encloses the blue shaded area. Here, I've regained exactly the same shape after equilibration, but the temperature has moved to a slightly lower value as did the negative chemical potential. And now I could repeat this and repeat and repeat, and in this way bring the Bose-Einstein gas to lower and lower temperatures, eventually probably across the transition. So this is kind of an idea which is under most experiments we perform. Now we could ask, can we actually use this, or can we actually use that to explore also out of equilibrium dynamics? And this is what I'm going to look at next. Now let's actually start with a question. Assuming that we are in equilibrium and can describe the system by only two parameters, here it's chemical potential and temperature, but you could also imagine any other parameters with which you effectively describe this many-body system, and ask what actually happens when we bring the system which starts somewhere in this plane spanned by the two parameters, which starts somewhere, how does it evolve in time? So let's suppose we have these two parameters, we can define them anywhere in this plane. Now we ask what's going to happen if we let the system go. So typically we will do a quench as the temperature quench before at some initial time, and then observe the closed system, how it evolves in itself. Now typically you would assume probably, as I showed and alluded to before, that it's going to move back into equilibrium. So what we'd expect is that wherever we start in this plane, provided that the total energy, for example, and the total particle number is fixed, we will end up always in the same equilibrium point, which is essentially defined by the corresponding distribution function I've shown before. So there will be a lot of loss of information when the system goes into that point, and only those which are fixed by the conservation laws, like energy and particle number, will stay and determine what comes out in the very end. So we now like to use these ideas, starting by a quench somewhere, then letting the closed system evolve and impose a few conservation laws to go to more general types of dynamics. And I will just take the same kind of sketch and illustrate with this that we could have also completely different situations where the point in the center is no longer the attractive fixed point of the situation, which represents a thermal equilibrium state, but it could also correspond to some transient state, which the system moves into before it eventually leaves it again and moves to final thermalization. So I've sketched this here very deliberately. Don't take this sketch too literally. By the blue lines going away from this point and moving up or down to thermalization. And of course, if you know about renormalization group theory from the description of equilibrium phase transitions and universality, then you recognize here a typical flow of an RG set of equations for these two parameters. We would generally say two coupling parameters of an effective theory. So the idea is that these flows, wherever you let them loose, so to say, wherever you start them, will get attracted by some partial fixed points. We call them non-thermal fixed points before the system then evolves in the end to some final thermal fixed point again, given the appropriate interactions in the system. And on the way to the non-thermal fixed point, we could have even other drift physics, which is not yet that universal, where we would say there are partial fixed points, pre-scaling, where the system already shows some signatures of this evolution, but it's not yet there. And I would now like to illustrate in the following, in practical examples, what it means to have such evolutions, such universal dynamics far out of equilibrium, at the example of a single component and a spinor Bose-again. Right, let's first of all emphasize that typically what we will see is that actually realistic experiments will not get quite to the non-thermal fixed point. I will illustrate this in a minute. Now let's come back to this picture of the distribution and ask what else could happen if we do a quench on the system. Remember, before I had done these weak cooling quenches where I just took away the few hottest particles. But we could, of course, increase this quench, make it much stronger, and take away much more particles, cutting much deeper into the distribution, for example, here, right down to the chemical potential. If that happens, you are ending up, also, if you do this, you are ending up with a distribution which is essentially box-like, and which is clearly far out of equilibrium. All you've done is you have filled all the modes up to a scale and then cut it off. And if you're in higher dimensions, because of the dimensionality factor, you will even see that there is some power law multiplied on top of that. So the distribution rather looks like this, which means that all your energy in the initial state is put to a specific non-zero energy scale away from zero. And it's absolutely localized there. Now, what happens after having done that? For that, we now need to, I wanted to say that you can, before I discuss this, let me just point out that you could also reach this very far out of equilibrium state, this box in the initial distribution, by some kind of instability, where you do not start with a thermal state, but you start with nothing, and create through a parameter quench a situation where all these modes get for example, populated in an exponential manner within very short time. And then their population stops because of some conservation. Then you're ending up with the same kind of distribution. And actually, we will have an example for that from our experiment in the fall. But now let's come to what happens after this, having prepared this initial state. Now comes the second step. The system is closed, as I said. Yeah, there's no bath around it. I'm really asking what happens to such a system simply through its intrinsic dynamics. So we take into account the interactions between the particles, but nothing else. So what you will have to consider are the conservation laws. The most important conservation laws, as we already alluded to them before, are typically energy and particle number. One is related to chemical potential, the other one to the temperature and equilibrium. And also out of equilibrium, we expect both of them to be important. Now, because our distribution typically looks like that, it's much higher at low energies down here and much lower at high energies. And remember, this is a double logarithmic scale. It is pretty clear that the energy is actually dominated by these high energy scales. Because the energy is essentially something like the particle number multiplied with the energy per mode. So if we say we have some energy per mode omega of p, then some energy per mode, then the total energy in that mode will be proportional to, for example, p squared times omega of p. Whereas, that's rubbish. That's not what I wanted to say. Sorry. So what I wanted to say is if the number of particles per mode is f of p, then the energy per mode is on the order of p squared times f of p, whereas the particle number will be just f of p. And therefore, the energy is dominated more by the high energy modes, whereas the particle number is more dominated by the low energy. And that's why when you now get a redistribution of your initial state towards a new equilibrium, you will have the two conservation laws being fulfilled at opposite ends of the distribution. You could also say it like that. Let's assume we have particles. Let's consider the particles sitting here at this initial energy. In order to redistribute them, you will need to, and in order to kind of push the particles down here, where they lose energy, you will have to deposit the energy somewhere. And you will be able to do that, conserving the total energy, by shifting a few particles down here, which gain energy. And because they gain energy, they can take over the energy of many more particles, which you had at this initial state here at the edge of your box initial condition. So that's the background behind this bidirectional transport. Now that's the first element of this non-equilibrium evolution. Now the second important element you can already see from the way I draw it. Because we have now two transports, one towards higher energy and one towards lower energy, we will expect to have two different shapes of the function. I remember in equilibrium, we had just one power law. So it was flat, then a power law, and then maybe some cutoff. And there was only one power law because there was no transport going on. Yeah? So microscopic balance, detailed balance, means that in each mode, the number of particles being scattered into and out of to the right is the same as in the opposite direction. There's detailed balance in every mode, and so there's no direction. Here we have a direction, and that now makes it possible to have different power laws in the UV and the infrared. And in fact, in the UV, we typically expect that this very quickly thermalizes. That's why we expect this power law to be close to something what we had before, the Rayleigh-Jeans law, T divided by omega. So you will have some local temperature defined by these high energy modes. However, here in the low modes, we have a steeper power law. Another question is, what is this power law? So that's now the main question we will have to solve by looking at the mathematics or numerics or experiment on such dynamics. Now let's actually consider also the time evolution of this part. Was also already alluded by the dashed line versus the solid line was that by time, the distribution shifts. Now, if I'm only concentrating on this infrared part, you see that the shape remains the same, but the distribution is shifted to the left and upwards. And you can express this mathematically by saying it follows a scaling form. A scaling form means that the function, the distribution function, at some momentum, at some specific time, is given by the distribution at a different time, at a different momentum, and both of them in terms of rescaling. This rescaling now means that you shift the distribution by t to the beta to the right or to the left, then effectively, so the later distribution, this is the dashed one, is expressed by the earlier one shifted to the left and upwards by this factor in front. And as you see, this defines two scaling exponents, alpha and beta, which now are, together with the scaling function fs, the only three informations you need in order to describe the overall evolution. Now, typically, the scaling function will also have a universal shape, similar as we have that in equilibrium, where you define some cutoff scale. Here I expressed it in terms of a momentum p lambda, and then the momentum scale, which kicks in only above this cutoff scale, and which goes like p to the minus kappa. No, sorry, I called it here zeta. Sorry, I should. I'm sorry. So there's now power law p to the minus zeta. So all in all, you see the time evolving distribution function is defined by a scaling form, so a function which describes its shape. That shape is characterized by a single exponent zeta and a non-universal parameter p lambda. And the time evolution, which is just a rescaling, is defined by two more scaling exponents, alpha and beta. So these are all the informations we need. There are three universal numbers, alpha, beta, and zeta, and one non-universal number, p lambda, which describe the entire evolution. So from that point of view, you see again that we have something universal. It does not depend on the details of in what system it is realized. All you need to specify are these simple mathematical characteristics. And at that point, it's very similar to what we saw before in the equilibrium thermal gas. Right, so with this, we have essentially set up the whole mathematics, the whole concept to describe universal dynamics far out of equilibrium. You can imagine that there are different kinds now of realizations. In particular, you could actually have different types of such self-similar rescalings. The one I described here in a simple form, actually, where there's again only one power law, is such that it rescales by shifting the distribution. So let's actually now cut it again here in two halves. Then the infrared part is shifted to the left and upwards. Here I also have the possibility to have a UV part rescaling that you could also have. What I want to emphasize here is that you should not mix this up what is typically called a cascade. A cascade, that's what you have, what you often have in turbulence, either in fluid turbulence or in wave turbulence. And here I show an example again of a transport which leads to the infrared in a cascade. A cascade is different from the self-sim evolution by the fact that actually where the power law is, the distribution essentially doesn't change any shape. The only thing what happens is that this scale here moves upwards and builds up the power law further and further in the infrared. You could also have this in the UV, and typically in fluid turbulence, you have this at the other end if you're not in two dimension. So you see the difference is that there's no, let's say, the left and upwards shift coincides in its quotient with the parameter, with this exponent, which here I call kappa. In this way, and that's now the important thing you should kind of take from this, the transport becomes completely local. And that actually makes it very similar to what we have in equilibrium. So if you look at maybe such a point here, then during the evolution, there is still kind of particles being transported up there. So you need to probably kind of winch it down there or drive it because these modes up here want to be filled. So there must be transport but the transport in and out of a particular shell, momentum shell, is the same. And because of that, the total number within the shell doesn't change. And that is different from our situation over here with the general self-similar evolution, which is not completely local. So also here, the distribution at these Paulo, at these scales in the center can go down. Well, that's all I wanted to kind of emphasize. You see, there's a plethora of different types of universal evolutions. The one we are gonna focus on is the self-similar one I'm sketching here on the left. Now let's come to an experiment. As I said before, realistic experiments operate here. So what do I mean by this? Let me actually go briefly back to this. So what we have in mind is this situation that we are in here. Actually, let's go and move on to experiment, and then I'll explain later on why we are not yet at the fixed. So let's take the experiment. Take a spin 1 Bose gas I promised to talk about, which means we have actually 3 Bose gases in the hyperfine quantum numbers +1, -1, and 0, which combine to an F = 1 state. So the symmetry of the Hamiltonian should follow this rotational symmetry of a spin state. You call this a spinor gas division. This is what we have in mind. And in fact, what we would like to do in the following is we would like to consider the situation that the particles are all in the 0 mode initially. And we have essentially a condensate in there. So we start with the Bose-Einstein condensate in the single Fz = 0 mode. The side modes, so-called side modes, plus and minus 1 magnetic numbers, are supposed to be empty in the beginning. What this sketch already also indicates is that we have here an energetic difference between the two. So we have applied what is called a quadratic Zeeman shift, which actually leaves the plus and minus 1 at the same level and shifts the 0 downwards with respect to these two. There will be also a linear Zeeman shift, but it's irrelevant. I can actually essentially divide this out, subtract it from the Hamiltonian, and just do as if there was only a quadratic Zeeman shift. Now we will use this quadratic Zeeman shift to quench the system. And in order to illustrate what type of quench we do, let me briefly go into the phase diagram of such systems. Typically, what you have is you have this quadratic Zeeman shift. So the Q is essentially a number which measures how far these two levels are apart. And then there's another important coupling. That's the so-called spin coupling constant. I'm not going to give you now the whole Hamiltonian because it's too formal, too much mathematics. Let me just say that this is the strength with which the spins interact with each other. Yeah. So imagine a Heisenberg model, a Heisenberg magnet, where you have spin times spin vector interaction, and there's a coupling constant in front, and this is the C1. Now, if you take these two parameters in the ground state, there are a couple of phases, and the phase we are starting in is this so-called polar phase, and you can actually see it here from the spinor, because only in this polar phase all the particles are in the Fz = 0 mode. Yeah, so this is, I should have said here, this is of course plus, no, I can't do it like this. This is +1, -1, and 0. So all particles start in the 0 mode, and what we will start off with is actually a negative C1, so we'll start on, run this red point. It's only a sketch. Now, starting there, we will now quench in Q to a smaller value, such that we are across the phase transition within what I call the broken axis symmetry phase. You can this phase is also called easy plane phase, because in the ground state, in that phase, the spin vector is actually elongated in the Fx, Fy plane. This is sketched here on this Bloch sphere. You can also read it off this spinor here. So you will have contributions in all three components and the plus and minus 1 will be equal. If you calculate then the spin for that state, you will find that it lies somewhere in the fxy plane. Now that's the new ground state, which should actually the system go into if we were at 0 temperature after the quench. Of course, we won't be so. We will start with all particles in the 0 mode, then shift the Q to a smaller value. That is, we shift it here upwards, such that it's much closer to the two side nodes. And that will create the possibility for these particles to be scattered in the plus and minus state, in the plus and minus magnetic subnet. When you now work out the mathematics, you will find this produces precisely what I called before an instability. So what we will get is this type of evolution we've seen before. There will be some scale. It'll be related to the final Q scale, which we choose, the final distance between the side modes and the central mode. And up to that momentum scale, we will fill all the modes, creating such a box-like initial condition. So exactly what we need in order to later on move towards a non-thermal fixed. I would like to illustrate how this looks like in the real system. What we will actually have there in this experiment is a simple, relatively simple quasi one-dimensional gas. So it's in an elongated trap. It's going to be kind of sharply confined in the transverse direction, such that the dynamics will be essentially one-dimensional. What I do here in the lower sketch is I give an example of the spin orientations in the xy plane, which will follow out of this quench. So you can imagine it's like you start with all particles in the 0 mode, and then suddenly you switch the potential in a way that it wants to run away in any direction. And it will do this in an erratic way, such that the new spin, after a short time, will be directed into some some orientation in the xy plane, and that's going to be relatively random. So what we will end up with is a random direction of these spins along the 1D gas, which creates this sort of wild excitations of the spin in the xy plane. Now let's have a look at some data, how this looks like. What they've done in order to measure this distribution of the spin in the xy plane is to switch off the experiment at some point, as they typically do. So they essentially stop with the evolution by rotating the system by 90 degrees. In this way, they rotate the xy plane into the yz plane, such that the spin is now no longer in this horizontal plane, but in a vertically oriented plane. And that has the advantage that I can now, by measuring the occupation of the different components, plus 0 and minus 1, I can actually measure the spin orientation into the z direction, and therefore with this in the x direction. So it's the typical way how they do it in spinor experiments. And they've actually developed this to a way, to a degree that they can rotate essentially around any axis. So now they can actually measure all the three components from the same, essentially from the same type of runs. Of course, in each realization, you have to fix the sense of rotation. Now the result is shown here, and what you see is these are the occupations of the three modes as a function of time. So the time points are 0 seconds, 0.5 seconds, 7 seconds, and 13 seconds after the rotation. And you see that there's some evolution. In particular, you see that initially there's essentially everything in 0. So this means that they have rotated without waiting after the quench. They have rotated immediately into the YZ direction. And that is essentially the box-like initial state which you see here with the spin randomly oriented in the direction. Now, and I should say, yeah, exactly. And then waiting a while before they rotate, you see that you get strong excitations. It's actually not true what I said. This zero is actually, there's no quench done yet. So this is after the quench where you see this random orientation. And then when you let it go, then you see sort of still some excitations on it, but they get more and more washed out. Now, we cannot really see what that means from this picture, so we need to go on and actually make a measurement of the spin structure factor. That is essentially of the occupation number of the spin excitations in this plane. And that is shown now in the two plots here. Once for the different times, simply as you measure them in the left panel. And you see that times are from 4 seconds after the quench to 9 seconds after the quench in color code. And you already can see that you start with a distribution which looks already like this universal distribution which we expect. And that with time, the distribution shifts to the left and upward. So what they did was to rescale all the later distributions by some guessed exponents, alpha and beta. And when they take beta to be around 1/2 and alpha to be about d times beta, where d is the dimension, which is here 1, you can actually rescale all the distributions nicely on a single universal curve as it is seen here in the right panel. So you see that during these times of the evolution, you actually get more or less a pure rescaling of what is here called the structure factor, which measures the excitations of the spin in the xy plane. Right, so with this, we have in fact observed such universal evolution in the spin 1 gas, and it determined the universal exponents for the time evolution, alpha and beta. We've also determined the kappa, which is roughly -2. I haven't sort of put it in here, but you can sort of read it off this part. Right, now the question is, do these results make sense? Now comes the job for theory, which we actually did before. So we had a prediction on the basis of theory derived from quantum field theoretical methods. Now, I don't want to go through all the details of that here in this kind of school talk, but like to at least give you a rough idea of what the principles behind the analysis are. And for that, I would like to remind you of what is called a transport equation in momentum space. So this transport equation typically runs under the name Boltzmann equation. The Boltzmann equation tells me how this occupation number of the modes, I go back here to a single component gas, do not talk about spin structure factor, but simply about the occupation number as I had it in the beginning of a simple single component momentum mode as a function of time. Now the Boltzmann equation tells me how that distribution evolves in time. And it does it in terms of a so-called scattering integral. This scattering integral tells you how the transport goes. Yeah? So transport is, as I explained in our example, a transport not in real space, as you typically have it at hydrodynamics, but it's a transport in momentum space. Yeah? So remember, we have this self-similar rescaling of this distribution function, which means I need transport excitations to lower energy. So my Boltzmann equation will tell you how it does this in a quantitative manner. Now, if you haven't seen such a Boltzmann equation before, let me briefly describe the main ingredients here. So what you have is that you first of all have to suppose what type of microscopic processes are possible. In our case, we have the typical elastic interactions, which means we have two momentum modes being scattering off each other. Let's call them P and K. And two other modes being populated after the scattering event, here I call them Q and R. So it's simple elastic scattering between pairs of particles, as it's the most basic process in weakly interacting gases. Now, in this Boltzmann equation, the scattering integral now tells me how this occupation of the mode P changes under the in and out scattering of particles from other modes. Of course, under this basic process. So what I have here is I have a sum over all the other three momenta. The momenta need to fulfill momentum conservation. So P plus K must be the same as Q and R. So it's elastic scattering. And it's also, that also implies that the energies must be conserved. So the two energies of P and K must be the same as those of Q and R. So the sum over all the three momenta will only take into account those processes where these two conservation laws are fulfilled. And besides these conservation laws, there are two other factors. There is what is called the T matrix. That is essentially a measure of the probability of the microscopic process, which we will have to put in. I haven't said yet what that is. That's just let's say, a probability to scatter from P and K into Q and R, or the other way around. And then the third important ingredient is this typical Boltzmann factor, which measures how many particles there are already in the modes contributing. If you haven't seen this typical type, let me actually emphasize that this what is called here wave-Boltzmann equation originally comes from what is called the quantum Boltzmann equation, where instead of this factor here, I have something like NP plus 1 times NK plus 1. And the same, of course, here for Q and R. So let's have a look at this kind of more general quantum Boltzmann equation and assume that NP is much smaller than 1. In that case, I can actually neglect these two as compared to the ones. And that means that actually this whole factor is 1. And not NP plus NK. In that case, all what is left is this NQ times NR, and here in the second factor NP times NK. That is nothing else but the normal Boltzmann equation you might know from statistical mechanics of classical particles. So from that, you see here that we do not have that limit because there's this extra factor NP plus NK in front. And that means that here we are in the limit that NP and that all the occupation numbers are much greater than 1. And what I can actually do is I can take the higher order limit. Right? You will see now when you take this full Boltzmann equation, then the order 4 n to the 4 terms, they are 0 because they're exactly the same in this term and that, once I've written it in this full form. So it's NP, NK, and Q and R minus NP, NK, and Q and R. That will go, that's simply 0. So what is left is actually the 4 terms where in each of them a single of these ones play a role. Okay? So that is called the wave-Boltzmann equation, and it's always important. So that is always important, wave-Boltzmann, when you have something like large occupation numbers as compared to the quantum one, wave-Boltzmann. And as we are here in the Bose gas, in the infrared limit, where we build up a large occupation number, we are confident that we're in this regime. So it's semi-classical in the sense that in each mode, there's much more than one particle, as is allowed for a Bose gas. And therefore, we have essentially such a wave-Boltzmann dynamics. Now that's the basis of our analysis. Now, all we need to do is we need to plug in our scaling form for n and can work out what the scaling of this whole scattering interval is, because you see the delta functions are homogeneous, so they rescale under a rescaling of the momenta. This rescales under a rescaling of the momenta. The factor of 3n's, they will rescale according to this scaling form here I plug in. And the same is true for the integrals. And all I have to assume is that also the T matrix will be scaled. But once this is satisfied, I can be sure that the right-hand side is rescaling. So it's homogeneous under rescaling of this external momentum and time with some exponent characterizing this homogeneity. The same is true for the left-hand side. And that means I can work out what the homogeneity factors are on both sides, and from that determine what the exponents are. Now that's the principle behind what we're doing here. And I would not like to go any deeper into the mathematics because that's going to be too technical in a second. So the only thing which is now left to discuss is what is actually this T matrix. And for this, it's important now to realize that you cannot take it to be a constant. If we would just take, for example, a Gross-Pilievsky theory with a constant coupling, then you would also find actually that T is nothing else but the coupling constant in the Gross-Pilievsky theory squared. But then you have a problem, because you see in the infrared, these distribution functions grow large. So at some point, because on the left-hand side, we have only one distribution function, on the right-hand side, we have three. We have the problem that T squared times N squared will typically be much greater than 1. And at that point, our approximation breaks down, which we've done by essentially assuming that there's only the simple elastic 2 by 2 scattering. I cannot go through the sort of details of what you have to do to get beyond. But let me actually tell you that what you find if you go through the corner field theory is that this T matrix now in the infrared will go down in order to cancel this divergence. And what it will look like is this just briefly sketched on this plot. So our T matrix squared will be a coupling constant squared in the essentially transfer momentum and transferred energy. And it will go down in the infrared exactly in the same way how our distribution goes up. Yeah? So if our distribution moves in time upwards, at the same time the coupling will go downwards, and it will also rescale in some characteristic way downwards, such that it makes sure that the total scattering integral remains finite. So that's kind of the what you have to do in order to describe these rescalings towards infrared momentum. Let me now just tell you, because it's too technical to go through all the calculation, that through this we find three relations. One from the comparison of from the analysis of this Boltzmann equation, and the second one we get from the fact that we need conservation law. So the number of particles wants to be constant under this distribution that gives alpha is equal to d beta. And then you can combine the two, insert the scaling exponent of the T matrix, which we can also calculate, and this way work out what alpha and beta are. And what you will find that then are two numbers. And what we will actually find is precisely, sorry, I should have not done this. So what we will actually find is precisely alpha is equal to 1/2 and beta is equal to alpha in 1D. So it's beta times d. So it's beta in one dimension. That's what we find. And in a similar way, you can also work out this exponent describing the fall off, and you will find d plus 1. So you will find 2. That is equal. That is actually the dynamical exponent, because omega scales roughly essentially like p squared. Right. So what we have from this calculation was a prediction which we found very nicely in these experiments. Now it actually, let me actually check, because my time is almost up. I should, yeah, that was anyway only to flash what the methods are. You can then look up the references on the slides. I would not like to talk about the low energy factor theory now, how you could alternatively work this out, but rather come to recent calculations and also measurements in this spin 1 gas as promised in the beginning. So what we've now done is we've done these simulations. We have done simulations of the spin 1 gas in one dimension in order to check whether also in theory our prediction was correct. So remember, the prediction we had was that alpha is equal to beta is equal to 1/2 and zeta is equal to 2. So what we did was we set up on a computer in a so-called truncated Wigner type simulation a calculation where we did exactly the same as they did in experiment. So we prepared by this quench of the quadratic Zeeman shift an initial state, an initial instability, which you can see here on the left. So this is, again, the structure factor they measured as a function of momentum. Actually, this is missing here, K, on a double logarithmic scale. And you see that up to some scale here, there is essentially exponential rise of the distribution initially, which brings up this type of box initial condition. And then at later times, which is seen in the typical curves of the universal distribution, you see this type of distribution forming and then rescaling in space and time, as is maybe also better seen by the colors in the right panel, where the yellow times are earlier times and the dark times are later ones. And you see that the distribution, it shows this bidirectional scaling now with a single power law in the center. Now, unfortunately, when working out alpha and beta, what we found, or maybe not unfortunately, but luckily, we found something different. Namely, we found that beta is on the order of 1/4 instead of 1/2. So here are the two exponents numerically. Beta is 0.26 and alpha is also roughly equal to beta. So the conservation law is fine, but it's by a factor of 2 of the experiment and the prediction from theory. Now, we worked on this quite a while. The experimenters repeated the experiment. In the meanwhile, and I'll not show their preliminary results, they actually also find parameters where they can go closer to 1/4, what we see here in these simulations. Now the question is, what does this mean? And I would like to give you some impression of what else, besides just having such a transport, you could have in such a system. And that's pretty nice. For that, I would like to look at the distribution now in real space as it evolves in time, namely of the distribution of the spin. So what I show here is always plots which horizontally are showing the x direction, so real space position in both of these plots, and upwards I show time. So in 1D you can do that, so you can nicely show how the system evolves in this plane. Now, on the left, we see the length of the spin vector in the xy plane at perp. So it's essentially the complex field fx plus fi fy formed out of these two components. So the modulus is something like the length in the plane. On the right, you see what is called the Larmor phase. That's the phase angle of this complex field vector in the easy plane. And then there are two plots which show essentially quantitatively how the spin is statistically distributed. Initially, here we are still in we have everything in the 0 mode, and then after the evolution, how it distributes in the easy plane. So that's the distribution in fx/fy. Now, what is important to notice is this funny structure in the phase. What is this? So we have this since a while. It's actually published in this paper by Christian Schmid, but we have only recently worked out what the specifics behind this pattern is, because we thought, looking at that, well, there is kind of, first of all, some straight lines in there, which go together with the speed of sound in these spinor systems. So there must be some objects traveling as we would also expect it in a single component Bose gas with a speed of sound defined by the system parameters. But we were asking, what are these objects? It looked maybe a little bit like kinks as given by some solitons in the spin direction, but it was not at all clear from this large noise on the top of it. Now, looking at that in the Fx, Fy, and Fz components separately, we first of all realized it's really nicely in the Fx and Fy plane, and that is not always so. Yeah, so we can also produce other initial conditions where we have much more in the Fz. But this typical quenches, it's essentially in Fx, Fy, and then we see these patterns in between which the spin essentially jumps suddenly, but it's still not very clear of what distinguishes these patterns. So what Ido, who is now working on this numerically, found out recently was that if he was looking at this phase angle, Larmor phase again, but not with this color code, but with a pure black and white code from -pi white to pi black, that you could actually see that in this two-dimensional plane spanned by x and t, there are some kind of phase defects. And there's a very clear one seen in this inset here on the left, where you can observe that the phase gradually increases when you go around that. Let me actually switch my color to red, then it's maybe seen more clearly. So the phase increase from -pi gradually to pi, and then suddenly it jumps. Well, that's like in a vortex. But remember, this is not in a two-dimensional gas where we could have typical vortices, but it's in time and space. So what we have here is a vortex in space-time. And we have actually not only one, we have many. Yeah? So there are these red and blue dots, and at the early times, it's a bit difficult to detect them, and the algorithm is also not completely clear, but at later times, it's pretty clear that there are sort of a dilute system of such vortex-like defects. And when we measure the winding number around our 1D system, which is periodic in the x direction, so J naught is the spatial gradient of the Larmor phase, and we integrate it over space, which gives us a winding number around this one-dimensional direction. Then you see that this winding number always jumps by 1 or -1 whenever such a vortex occurs. Now, these vortices are known as so-called instantons in quantum field theory. So they are a type of phase defects in space and time, and they essentially mediate between a system, for example, without a winding number and one with a winding number. So they essentially make some macroscopic scattering in the space of excitations. Typically, this is discussed in equilibrium in the context of the Mott insulator transition in a lattice, but I'll not speak more deeply about it. I just mentioned it. Now, it's nice to see that these instantons play a role here, and what we made then is statistics of the instantons in time, and essentially the probability to have an instanton in a certain window of time as a function of time. Again, here it's on a lin-log plot, and what Ido found out that this is essentially a stretched exponential. So if you plot the logarithm of this p of t as a function of time, on the double log plot, you get a nicely straight line with some exponent delta, such that this function is something like e to the minus t to the power delta. So this shows that there is some universality in the statistics, not only of the excitations we would describe with our Boltzmann equation, but there can be much more structure on top. And what we come back with this too is some kind of coarsening dynamics we've discussed in many contexts before, also in superfluid turbulence where you have vortices which get diluter. Now we have it here in this one-dimensional spinor gas. With this, I'm actually now at the end. I would not like to, I could say more about the vortices in 2D, but because of time, let me actually stop here. And I've actually used up a whole hour, which is bad, but I hope you got something for it.
Hello?
Yeah, hi. Okay.
Thomas, thank you very much. Very nice talk. We still have time for a few questions, please.
Hey, Thomas, thank you very much for that nice talk. And I have two questions I want to ask. One of them is, normally we're dealing with those systems like, those cold atoms, and doesn't matter if we look spin or anything else. And I just want to know from you if there is any difference between equilibration and thermalization. Mm-hmm. That's my first question. Mm-hmm.
Yes, I mean, you could, of course, kind of go very far now in the answer. The first thing is, if I talk about equilibration, I would talk about some very well-defined attractive fixed point. Yeah, so equilibration means the system goes there and never leaves again. Whether that's a thermal fixed point or something else is a different question. So there are people have discussed a lot, for example, these generalized Gibbs ensembles and so, where they showed that if you have more than the simplest conservation laws, you could have equilibrated systems which show more non-universality, let's say it like that, depending on this higher number of conservation laws. That can happen, and in particular in 1D systems, that's typically the case. That's kind of the first thing I would say. Then you could ask, what we see here, is this also some kind of equilibration? And I would say also the move towards a non-thermal fixed point is a kind of equilibration, in the sense that you have many aspects which are very much alike the thermal fixed point. So as I described, there's this transport which goes, which can even fulfill detailed balance, but in a directed manner in turbulence. Or in our case, you have still transport going on, but it's critically slowed, so it's only a power law in time. It's no longer, it's not exponential in time. It's very slow, but it's universal in a manner very similar to what you have in equilibrium. So there's a simple universal function. There's a few universal exponents, and that's it. It only depends on these, and they are somehow related to the symmetries in conservation laws. So from that point of view, you could say it's very similar to equilibration. This evolution towards a non-thermal fixed point, as you would otherwise have towards a thermal state. Now, you could go further and discuss, are there, for example, some entropies which define these states? I think there are. Yeah, you can probably define. They're actually working with that at the moment, that one can find these more generalized linear entropies, which then characterize these kind of transitional, I would say, pre-equilibrated states.
Okay. Now, the second question, the first one is, I understand what all the arguments that we needed a scattering involving, and I saw that you say that the rate in which the distribution changing time depending on that, let's say, integration or functional of the density, which has to take into account the conservation of momentum, energy, and everything. Mm-hmm. Now, don't you think that the system is simpler than that, and maybe it is looking for a minimal effort to be in evolution, like it is looking to where I should vary less in momentum or in time, and then maybe I can reach the same arguments that you have done with that functional of the density?
So what you're alluding to is probably sort of simpler effective theories of this evolution, which you can write down typically. I mean, I don't know, for turbulence and this kind of stuff, like already fluid turbulence, but also in wave turbulence, people often write down very simple conservation laws describing the transport. Like in this wave turbulence, people typically write down just a continuity equation, saying, okay, I have a local transport, but in momentum space, so let's just write down a continuity equation here, what I described here. I can say, okay, let's just go to this point and say, the distribution here, dTn, is given by the divergence of a current, and that current describes what flow I have. Yes, I'm pretty sure this is possible to a very good approximation. I'm also pretty sure that in many such cases, you can do that in the end. And maybe let me give you one example we've been thinking a lot about recently, and that is coarsening. Yeah, so coarsening is behind what we had here. Yeah? You create a pattern, and then the pattern evolves, increasing the scale in there. For example, if you quench cool a magnet below in temperature, then you create these Weisian areas, and they will then afterwards grow in time and in some algebraic manner. Now, the question is, can I write down also a simple law for that, like this one? And typically people do this. They write down these type of diffusion type equations in coarsening, like the Kahn-Hilliard or Allen-Kahn equations, which are like Ginzburg-Landau equations with a conservation law imposed. So this is kind of the typical thing. So I think you can do this in the end. Now, what our interest in here is that is not so much kind of what you can do to write down this in the most simple way, but to understand what kind of is behind these effective descriptions, and maybe from there get to new effective descriptions. So by going back, I mean, it's of course kind of a hell. You have to say, I have a closed system, there's no bars, nothing whatsoever, so I cannot use all these nice statistical mathematical methods. But I want to have it all in the system, so I need to go deeply into the nonlinear interactions between the systems. This is what turbulence people in hydrodynamics, I think, have not yet managed to do for the simplest kind of turbulence in a fully consistent manner. So it's hard, I agree. And I also agree that you're right. You should be able to get to simpler descriptions at the end. But maybe one can get systematics to get more sort of concisely, and also maybe find new phenomena in this way.
Okay, thank you. More questions? If not, I'd like to thank you, Professor Thomas Gasenzer, again.
Thank you very much.
Thank you, Professor.
All.
I expect that you can follow with the program of the school. Follow us. Thank you very much. Bye-bye.
Thank you. Okay.
Ele está falando com a Thalita? Thalita? tirar só para falar. Marcelo.
Hear me?
Okay, we're going to start. David, can you hear me?
Yes, I certainly can, Vanderlei. How are you?
I'm okay. Nice to see you. Thank you very much for accepting giving this talk in our school. And we have a part of the participants here in the auditorium and part of the participants following the talk by YouTube. And that's necessary because of the condition that were imposed for the realization of the school. I'm going to just do a brief introduction to Professor David Pritchard and then let him go. I hope he still hear me. Are you hearing me, David?
Yes, I am, Vanderlei.
Okay. So
I was hearing you twice because I've been attending the meeting via the usual way of using the browser. So I had you coming in 2 times.
Okay. So Professor David Pritchard is a very interesting figure. He studied in the Caltech Institute of Technology, and then he got his PhD at Harvard, as Dan Kleppner explained today. And then he became a professor of MIT. And as a professor of MIT, he always had a large amount of students, very motivated. And David is one of the smartest physicists I know, because he always have good ideas and he knows in what experiment to go. Just to give you some example, he is one of the pioneers in the study of atomic beams as waves, atomic waves interferometer. And he did a wonderful sequence of experiment. And maybe the most complete experiment in interference of matter waves was done by David, and still being explored in many things. He's always been ahead of his time, so we are still waiting for the big applications of the matter wave interferometers. But this is not all. David gave you the seminal ideas of the magneto-optical trap. And we could not do almost anything we do with cold atoms if we didn't have this step of keeping the atoms by radiation pressure and forming the magneto-optical trap for further steps, putting in magnetic trap or anything like this. But David also introduced what today is called Pritchard trap, which is this nice combination of magnetic field that allow us to keep atoms with finite spin on a magnetic minimum. And many other things that David contributed, and that today the field of cold atoms is really a strong field because guys like David Pritchard. And David Pritchard is being recently chosen to be an honorary professor of our university. And I anticipate that I want to already invite you all to see the ceremony of giving the title of honorary professor to Professor David Pritchard on 25th of March in a special ceremony of our congregation. Okay, David, so, you know, David has been the advisor of many people that got Nobel Prize, and that really established the field of Bose-Einstein condensate. And I remember when I started to work with David as a student, I told him, I want to do something in condensed matter. I don't know if you remember, probably you don't remember anymore. And then he told me, look, those cold atoms, they may condense it in a Bose condensate, and that will be condensed matter. And for sure, you know, today we know that a Bose-Einstein condensate is much more than only condensed matter. Is a workbench for all condensed matter physics in many sense. So David, thank you very much for giving your time to us. And now I'm going to give you the word so you can give us the talk about these radiation forces and everything that took us to the stage where we are. Thank you.
Well, thank you very much, Vanderlei. Yeah, it was nice of you to mention all the experiments that I did that worked, whereas there were also some that didn't work. Okay, now I hope that you can see my introduction here, light forces, atom optics, interferometers, at this school. Can you see that okay, Vanderlei?
Yes, David, we can see perfectly. Go on.
Okay, so it's great to talk here. I've been looking at some of the talks on YouTube, and I really feel, boy, I should have spoken earlier, and that way I wouldn't have offended everybody by saying stuff that's all old to everyone and people have mentioned in their talks, and maybe not mentioning something that I should. But anyway, here goes. Yes. So I have to say it's wonderful to see, at least on the video, so many old friends. And of course, all the old friends that I have now were once much younger and in fact untenured. So here's an example, in case you don't recognize right away. This is Dan Klepner, and this is me back in 1967 on the day that I married this woman here, whose name is Andy Pritchard now. And many of you, if you have been here, have met her. Okay, so one of the big things that started me getting interested in this field was that I knew lasers were going to revolutionize atomic physics. That's why I got into atomic physics for my PhD. And even though then the lasers weren't tunable. And there was a field of light forces on atoms. And back in 1985, it had the ratio that you can see here between theory and experiment. And whereas I thought it was a probe of basic physics, and I thought you might be able to do some nice light force engineering, take traps and atom optics and interferometers and so on. Most of the theory of that time I didn't think was too great. So here's a page out of Physical Review, and I'm not going to tell you what this little term here means. I'm just going to go on to the next slide. And what I want to do is talk about some of our experiments, very early experiments on the coherent manipulation of atoms. And what I'm going to talk about is what happens when atoms encounter a standing wave of light. Now, I'll tell you in a few moments why I got interested in this, but at the time, before that, I had been doing scattering of atoms from other atoms, and I was very used to thinking in a very classical way. Here comes an atom, here's a mirror, here's the electric field, and the atom comes along here. And now if you know what happens when an atom's in a very intense field, it gets into a dressed state. And it has a dipole moment so that it either has plus or minus energy according to the E field. So here it is. And now you think, okay, you're scattering on this potential. Think of it like a hill. This is the top of the hill. If you hit it right there, you go straight. If you hit it where it's steeper, you start bending. And if you hit it right here where it has maximum steepness, then it has maximum derivative with position, then you get a maximum in the deflection. And you won't have any atoms that are deflected more than that. And then when you go down here, you'll get back through zero and you'll get atoms over here that are deflected the same amount in the other direction. So you should see that it's got a maximum and a minimum, and the pattern should look something like this. Namely, there's a singularity at the maximum deflection and at the minimum deflection. Well, that's when we think of atoms as being in a potential. What if we go one step further, as we have to? When he was a young man, in fact, doing his PhD thesis, Louis de Broglie wrote that if light, which we thought of as a wave, behaves as a particle sometimes, then maybe things we think of as particles behave as waves. And he suggested that the wavelength for a matter wave would be Planck's constant divided by the momentum, and proceeded to write a thesis about that. It was rather a short thesis, but it proved to be the basis of most ways, of the ways that we think about quantum mechanics using the wave function. The wave function behaves according to a wave equation, to Schrödinger's equation, which is, yeah, it's a first order equation, but with imaginary component and so and so. But it basically tells you about waves. And so now you have the classic two-slit experiment, where the wave can come along and it passes everywhere. It goes through slit one, it goes through slit two. And when the waves come back together over here where you're observing them, sometimes these come together, psi 1 and psi 2, the path here and the path there, have the same amplitude, and the same phase, they add coherently, you get a big signal, and then right next to it, you get a small signal, because you always have this interference pattern here. Now, if you think about this analogy here are two paths and they can interfere, and then you look back at the picture we just had, now you might realize here that if I look at an angle that is less than the maximum or the minimum deflection momentum or angle, then I have two paths that will go at that at exactly the same angle. And since this is a coherent process, they will interfere. And if they have a separation D here, the interference pattern will have oscillations with delta theta is equal to the de Broglie wavelength divided by this distance D, irrespective of the potential in the middle. That's a paper that I wrote back when I was a kid. Okay, so now we have to modify our ideas. If we look at those waves, well, we will see that in fact, there are maxima sort of in the right place, but there are interferences in the inside. And this is exactly the same phenomenon as when you look at a rainbow. You'll see in the sky, you'll see the rainbow. You'll see that it's dark outside, there's nothing here, and that it's light inside. And of course, you will see the colors here from this large peak here. But many times you will see right next to it another rainbow, which is called a supernumerary rainbow. And that corresponds to this peak here. And sometimes maybe once or twice in your life, you'll get to see the double peak. Okay, well, that's not all. We're still thinking semi-classically. But now we realize that the picture I showed only had one wavelength and of the light. But in fact, the light extends for many wavelengths. And so there is the possibility that the atom can diffract through the first minimum of the light wave, or the next minimum, or the next minimum, and all these will add up, and they will, and this is a diffraction gradient, and so they will not send atoms to all angles. There will only be a few angles. So now we go through this pattern again, and we see classical, semi-classical, treating the atoms as waves when you go through one wavelength. And now when you go through the full, you take the potential as periodic and go through the full semi-classical treatment, then instead of getting continuous distributions, you have these discrete contributions. So this is kind of the physical way that I learned to think about interferometry from my work in scattering atoms. Now, the usual treatment for this is called, well, it was first done by Kapitsa and Dirac in the case of electron scattering off light. It was also done by Raman. It's called sometimes the Raman-Nath regime. And also Bernhardt and Shor actually did the calculations that are shown here. And as you can see, this is very much like the pattern that, that we calculated semi-classically. Okay. All right. Now, how do we get such nice, sharp lines when we know that when an atom decays spontaneously, it spreads, the photon can recoil in any direction, and therefore the momentum is in general blurred? Well, okay, there are three processes, and this was known since Einstein's 1917 paper. There's absorption, there's stimulated emission, where the momentum is minus the photon momentum that's emitted, and then there's spontaneous emission. And he showed that the average of the momentum from spontaneous emission is 0, but its standard deviation is h bar k squared. Yes, the first part of that paper, the 1917 paper, just shows that there are three processes and gives the relation between absorption or stimulated processes. And the spontaneous and the stimulated processes. Absorption can be regarded as a stimulated process also, because it wouldn't happen if there weren't any light. But in the second part of the paper, he considers momentum transfer. And in fact, that's really the first radiation cooling paper, because he showed how a black body radiation would slow down an atom that was placed in the cavity. Okay, and when you see the sharp patterns, the one like the one I just showed you, it's a sign that you're having absorption and stimulated, but no spontaneous emission because it hasn't blurred out the data. Okay, so now I'm going to show you, maybe I'll make this distinction a little clearer. For spontaneous emission, you think of, and the forces associated with them, you think of the photons bouncing off the atoms. This saturates when the force is, roughly speaking, the natural decay rate over 2 times h bar k. It's incoherent, it heats the atoms, and the atoms interact very strongly. 1/10 of a watt of laser power can saturate atoms over an area of 10 square centimeters. And so it's obviously the best way to push atoms around, but as I said, it's limited here. Now the stimulated emission, this is really when the atom interacts with a potential. The maximum force is just proportional to the gradient of the electric field, and that can be as big as possible. This force does not saturate, so it can be incredibly strong. It's coherent, which leads to the possibility of atom optics. But it's weak. If you have 1/10 of a laser, of a watt of laser, it will be able to apply the same amount of force over only about a square millimeter. Okay, so incidentally, as you tune off resonance, you find that the stimulated goes as 1 over the line, 1 over the detuning, and the spontaneous goes as 1 over the detuning squared. So if you go farther and farther off resonance, you will lose the spontaneous emission and become more and more coherent. Okay, now the first experiments that were done by this, in this with a standing wave, were done by Toshiki Oka and his collaborators back in 1979. And they did not see 2 symmetrical peaks, as the theory that I just showed you predicted. They saw only 1 peak. And in their paper, they said, the combination of absorption and stimulated emission of the 2 oppositely traveling waves results in a net deflection of the beam. The observed magnitude of the beam deflection and its dependence on the radiation power agree with the calculation based on the random walk picture that the 2 traveling waves, plus and minus, are utilized randomly in the stimulated emission and absorption process. And that was published, and it was published because it, in spite of being totally wrong, once you have absorbed a photon from one wave, you are in the excited state and you have to then stimulate the next one. But it's much more complicated than this. And I have to blame the fact that it's imprinted all on the failure of the referee. And I have to confess that I was the referee. And when I saw it in print and read the article carefully, I realized that this couldn't be correct. I'd looked a little bit at some of the literature by then. And I decided, okay, fine. So if a fairly knowledgeable person like me fails completely to understand a paper that he's supposed to understand and referee, maybe there's some interesting things in this field that haven't been discovered yet. So I, at that point, started doing the same experiment, except better. And in fact, these are the first data that we got. And it was about 4 years later. And this is Phil Moskowitz, and I don't remember if Phil Gould is on this paper yet. So we actually saw this pattern that was split. And also we saw what looked like these single photon peaks. And that was a little surprise to us because I wasn't sure, I'd only been thinking about it the way atoms were, and I wasn't sure that we should see them. All these detailed calculations hadn't been done then yet by Bernard and Shore. So this is our apparatus. We get about 30 microradians of deflection. So our apparatus is almost 3 meters long. The slits were less than or equal to 10 microns. And when we got this going better, we, by 86, then we could see that we were having just these peaks here. And these peaks are at these are multiples of 2 h bar k. We are not seeing a single h bar k. We are seeing 2 h bar k. And that's because the atoms start in the ground state, come along, they adiabatically enter the field, and get some deflection, and then they adiabatically decay back to the ground state. So no atoms are excited in this process. And we could we could see these peaks. And in fact, we could get good agreement with the power shown with the graphs as I showed here, except we had to arbitrarily lower the power that we could measure quite accurately by a factor of 2. And that's because it's extremely difficult to make good standing waves with cylindrical optics and a retromirror. Cylindrical optics are just not, it's very, very hard, especially back then, to get cylindrical optics that were good at lambda over 4 or lambda over 10 or something like that. And so I suspect, and then of course you have to have the beam that's reflected back on the incoming beam be exactly on it. If they don't overlap, then there's no standing wave. And if they do overlap, you're sending the power right back into the laser, and it's likely to screw up the mode structure of the laser. So it's not easy to make a good standing wave, and I think that's what really happened to Oka to get his anomalous and now clearly incorrect result. Okay, so I'll show you one of the better cases where the theory and experiment agree. Okay, that's great. Now, let me go on and say that the Pritchard was the best precedent at that time. It's also called the Raman-Nath region. And it's also an impulsive region. You ignore, if you think about it classically with the atom going through the standing wave of light, then the atom does not get deflected substantially. The approximation is the atom doesn't move sideways in going through that. And so it's just getting an impulse in one direction or the other that only depends on the entry point. Now, if you have this short, if you really did it in the pulsed mode, then there would be uncertainty in the frequency of the laser. And the fact that the atom now had the same momentum coming along, but in addition, it had some transverse momentum from the light. So therefore, it had more kinetic energy. That wouldn't bother you because the uncertainty in the energy of the photon due to the short time would be enough to cover that. But we're doing it CW. We don't have a short pulse. The beam is on all the time. The laser is on all the time. And so we should have delta E is 0. But focusing, okay. So how do you explain this? Well, the idea is here. If you have the waste focused down so that when the atom's traveling this way across the light beam, when the atom goes across here, it goes across it in a very short time so that you can satisfy this condition, then that means that there is light coming in at all kinds of different angles. And so, in fact, if you want to deflect the atom to this final momentum, all right, you use light that's going in that direction. If you want to deflect it to the next peak, you use light that's bent a little bit more. And you can get conditions that agree with the theory as well as I showed. Now, what happens if you lengthen the interaction region? Well, the answer is you get into a Bragg scattering region. And here, your interaction time is longer than this. the you still can suppress the spontaneous emission by going off resonance. The longer interaction time means, though, that even in the pulsed experiment, the kinetic energy has to be constant. So you can make momentum and energy constant if you go from here to here. But now remember what that really means is here's the initial momentum. This is the axis of the machine. And now you see that the laser has to be tilted a little bit. And when you do that, you get this asymmetric pattern that it scatters over to here, which is 2h bar k. This is first order Bragg scattering. And we also demonstrated second order Bragg scattering. So these now, I mean, these curves look so crude compared to what everybody does now, which is to trap the atoms in a magneto-optic trap and then zap them with a Bragg pulse and very, very selectively just take part of that cloud and transform it over here, not adding any thermal energy to it, but just making it in a superposition of some atoms here in one state and some atoms here, well, either in the same state if it's Bragg scattering or if it's or Raman scattering, they might be different frequencies in different states. Okay, now let me give you just an example of why this is a challenge and also why it is an interesting challenge. I mean, some things are a challenge and they're not even that interesting if you did them. But in this case, the de Broglie wavelength, the number that I keep in my head is 25 angstroms divided by the mass of whatever it is in atomic units and the energy in degrees Kelvin. So if you have a mass 23 sodium atom at room temperature, you get a de Broglie wavelength of 1/6 of an angstrom. Well, anybody knows that light is about 6,000 angstroms. So look at that. You've got 36,000 times smaller wavelength. And that certainly suggests that this large ratio suggests that an interferometer for atoms might extend the precision of optical interferometry, as well as opening new paths of research. Now, the way we actually built our atom interferometer was after doing another piece of atom optics. And that was that in 1988, we were talking with Hank Smith at MIT, and he makes gratings by a holographic method. But after the talk, he gave a talk and we gave a talk in this MIT meeting. And then we went to lunch together and we found out that he made transmission gratings. I've been thinking of trying to do like Peter Tönnies at the Max Planck Institute, some diffraction off surfaces, but surface diffraction is messy because just the least bit of oil is going to totally mess up your system and the atoms either won't bounce or they won't be bouncing off the periodic clean crystal that you thought. So the transmission grating is, well, it's just a piece of silicon nitride with a hole in it, with a bunch of slots in it. The slot, this is the front view, this is the grating that the way the atoms see it. And these are the support bars, and these are spaces. The black space here is transparent. There's no material there. And so the atom just goes through. And then actually this thing is made on a silicon nitride membrane where silicon nitride wafer, it's made on a silicon wafer. The surface is made into silicon nitride by an ion etching process or ion implantation process. The pattern is made in the silicon nitride. The silicon itself is etched away. And this is a view of the edge of the grating. And the next picture here is the diffraction grating that we get from this grating. Now this grating here is one that we made. The one that Hank lent us, was made out of gold, and it was 400 nanometers. And then we made some that were finer that were made out of silicon nitride. They were 100 nanometers. And we got this diffraction pattern here. And notice that this is the first order peak here. The second order peak would be 0 if the open fraction of the grating were exactly 1/2 and the atoms didn't interact with the grating at all. And so what you can do is design a grating where these 3 peaks are basically everything. And these, well, now, this is first, second, the third order peaks are down at least an order of magnitude, and everything else is down probably another order of magnitude. So then you get very nice patterns. I think I'll just skip over this. This just shows that changing the velocity changes the angle. Now, it's one of the things that's interesting, fundamentally interesting, is we are diffracting a particle, and the particle has a de Broglie wavelength of 1/6 of an angstrom. But the particle is a sodium atom, which is something like 3 angstroms. So you're describing this big fuzzy ball with a very, very small de Broglie wavelength. And in fact, if you work out the coherence length in our beam, it's only 1.2 angstroms. So just try to put all of those things into your mind at once. Here's this wave. The de Broglie wavelength is very short. The coherence length is still quite short. And what we're talking about is something that's quite a bit bigger than both of them. And also the particle has many internal states. So I'm just going back to our apparatus now and saying, okay, let's take the next step. Let's make this into a 3 grating atom interferometer. This is the diffraction pattern apparatus. And now we just extend it, and we have a collimator, and we make the first grating, and it makes these 3 paths, and then we add on another grating, and then 2 of these patterns interfere. And actually, the way we detect it, the way you detect it in the textbook, is you make a very, very small detector, which would have to be much smaller than 100 nanometers. That's a pretty small wire in order to detect the interference pattern. But there's a much better way, and that is to just put a 3rd grating here and use it as a mask. And as you move it for a while, here you get to the point where these 2 incoming waves make an interference pattern, and you have maxima along these lines where these circles are drawn. And if you hold this 3rd grating at this position, then you will have a lot of intensity that goes through to the detector. And if you move it just half a grating width, in other words, just 50 nanometers, then it will block these maxima, and you'll get a minimum in the transmitted intensity. So you get a pattern that looks something like this. And these are the fringes, the first that I showed you, the first one, the first experiment that worked. And when we got everything going with our 100 nanometer gratings, then we got signals like this. And actually, if we used a helium carrier gas, we could even get a lot more. So the first thing is, gee, the hyperfine states didn't bother you. You had all these different hyperfine states. We didn't select those, and yet we got nice fringes. Well, hey, maybe we could put molecules through. Now, the sodium oven, if you really run it hot, and especially if it's a supersonic oven, it will have quite a big impurity fraction of sodium-2 molecules. But they're going the same speed because they're all in the same flow, but they have twice the mass. So they have half the de Broglie wavelength. So now what would the diffraction pattern look like? It would look like this. You see the pattern. This is the sodium and some sodium-2. And then in between, you see the sodium-2 molecules. And so, well, maybe that's not so convincing. But what if you just took a laser and blew away all the sodium atoms? Then what you have left would be the sodium-2 molecules. And this is what you would see. And so that's the sodium-2 molecule diffraction pattern. And now if you want, you can do all kinds of experiments with the sodium-2 molecules. We stuck pretty much with sodium. And so now I'll, not show you the idealization, but here's actually a picture of the apparatus. And this is the source, and the collimator. This is the pumping for the get rid of all the gas from the supersonic source, and then you have the gratings here and here and here, and the detectors down there, and you can put laser light in here to optically pump it or whatever you want to do. So I would just say, it's got 5 vacuum pumps, 50 wires into the vacuum, vibration isolation, and so on and so forth. One of the cools, and we have the whole interferometer on a breadboard, which I'll show you in a minute. When we wanted to show that atom interferometers are very good rotation sensors, we simply hung this thing up from the ceiling. We put lots of lag bolts in the concrete ceiling, and we hung the apparatus up, and then we made a way to rotate it slowly, and it could detect I think it was a 1 or 2% of the Earth's rotation rate in about a minute. So it was very good rotation sensor. Anyway, so this is in fact the gratings with all their holders and manipulators, and then the grating is just in that little tiny region there. And then we had an optical grating over on the side to measure the position of the atom gratings. So I won't go through that. And there's another picture. So the atom beam comes out and makes a lot of interference patterns all along. And there it is. Okay, so I should have taken that picture out. Now, we actually had enough with our 1,000 angstrom or 100 nanometer grating period. We had enough deflection such that we could make an interaction region, which is shown here. There are 2 big plates and a very thin foil here, about 10 micron foil, I think. And so we actually had the atom paths going on one side or the other side of this foil. So now we had the atoms isolated in the 2 sides, and we could put an electric field on one side. And well, now what's your view of what's happening in the interferometer? If you think, is there a phase shift? Yes, there's a phase shift on this side, which is proportional to the polarizability there and the field squared and the length and divided by the velocity and so on. And so you should see a fringe shift because on one side, the atom is interacting with the electric field, and on the other side, there's no electric field and there's no dipole moment. So the atom splits up coherently, comes back together, and now we see, as we change the electric field, we see the position of the fringes shift, and the shift is proportional to the square of the field. And so this shows it accurately. And so as a result of this measurement here, we could measure the polarizability of the sodium atom to about 0.3% when we figured in all the uncertainties, like calculating exactly the size of the field and the voltage. You can know the voltage accurately enough, but the field and the effects at the end cause a little bit of uncertainty. Now, of course, there is a lot of theory that goes with this. Basically, the theory for polarizability, which is what you measure out of this experiment, is second order perturbation theory, which you can express in terms of the oscillator strength and so on. But given that it's a sodium atom, there are lots, it's quite a complicated calculation. And so there are lots of ways to approximate it. And so there was the history of lots of different theories and a couple of measurements back in the mid-70s. And then finally, we made this measurement in 85. And then I'll just tell you, these measurements, some of them use Hartree-Fock, some of them multi-configuration, some just the oscillator strength, some pseudopotential, some variational methods. And as you can see, they vary by 10 or over here, 20%. I mean, it always bothered me that even with something as simple as a sodium atom, uh, with 11 electrons, and almost all of the effect of the polarizability coming from the valence electron, at least at that time, it hadn't been treated to even 0.1%. And you sort of wonder, is the quantum theory that we're using, is it really the ultimate theory if it doesn't describe in a fairly natural way the pattern of these 11 electrons, which is to say the way the patterns of the world? Anyway, I want to ponder with you one more thing, and that is the which way experiment here. The idea of the which way is, can you picture this atom as going through one side or the other, or must it have gone through both? Well, you observe fringes, and the classic interpretation of that is that it went through through both sides. Otherwise, you wouldn't have seen the interference fringes. On the other hand, what you're getting from the electric field, the phase shift is as if the atom went only through the electric field. If you try to imagine how the atom could spend only half of its time in the electric field, or if split its mass and charge in the field, you would get far, far, far from the right answer. And so you can't imagine that it's splitting. The best picture to take is the Feynman idea that quantum mechanics is the sum of the amplitudes of each individual possible way that the system could have gotten from where you prepared it to where you measured it. Okay, so that ends this, and then now I'm going to talk about atom cooling and trapping. And so I'm first going to just rhetorically ask the question, why trap and cool atoms, or ions for that matter? And of course, the historic reason was atomic clocks. Lengthen the interaction time, reduce the second order Doppler shift, reach low temperatures so the atom-atom collisions are simple, they're S-wave. Get high resolution spectroscopy from the continuum. The atoms are so slow in a Mach that their Doppler broadening is less than the natural line width. And so the continuum, if you make a molecular transition from a continuum to a bound state, or from a bound state to the continuum, it's sharp. It's natural line width limit. It's not Doppler limit, it's natural line width limit. So you can have high resolution spectroscopy. There was lots of speculation about things called Efimov states in weakly bound systems. There was always the pot of gold, as we used to call the end of the rainbow, the Bose-Einstein condensation and the condensed matter. And of course, the reason we do this stuff is because it's challenging and it's fun. So what do you have to trap neutral atoms, or to trap anything for that matter? I mean, it could be if you're trapping animals at the town dump, which I did when I was a kid, mostly rats. Anyway, you have to have two things. You have to have a force that will push the thing towards the center of the trap. Whichever way it goes off, it has to have a restoring force, a three-dimensional restoring force. And if it only has the restoring force, like, you have a surface here and it has a dip in it, and you roll a ball along and it'll just go down the hill, and then it'll be going fast. It'll just roll right up the hill on the other side and out. So you have to have some way to damp it down when it's in the middle of your trap. So these are the two things that you need. Now, it turns out nature's opinion was that it was fairly easy to cool things, either with Doppler molasses or evaporation, but that it was difficult to trap them with light forces. And so I'm going to go over this fairly quickly. Laser cooling, the idea was if you're in the lab with a yellow sodium atom and slight orange lasers, you get an equal force from each side. Now, if the atom is moving, then it will shift these guys closer into resonance to the yellow and these guys farther into out of resonance. And so you'll get more photons coming in from the front. And so you naturally have a way to slow atoms down. And this was demonstrated by Ashkin and Shu. It was demonstrated really earlier by Phillips and Metcalf because they not only slowed the atoms with the photons, but they also, owing to the way their slower worked, it cooled them off as well. So now the question is, so there were several ways known of cooling the atoms, but then how did you trap them? And Ashkin by himself demonstrated and won a Nobel Prize for trapping glass beads and then bacteria. And then with Steve, they trapped atoms. But the volume was just a few times 10 to the minus 11 centimeters squared, just fractions of a wavelength or a wavelength on the sides. And so it's obviously, since as I pointed out to you earlier, the spontaneous forces are about 10,000 times stronger than the stimulated forces. Hey, let's figure out how to use the spontaneous force to get a larger value trap. But it won't work. And there was a long history of people like Minogan and others who came up with schemes to use lasers to use the spontaneous force in what they thought would be a configuration that would trap atoms. For instance, light coming in from all four corners of a pyramid, these two here and those two there. Well, then Ashkin would provide some careful calculations, and he'd show that that scheme didn't work. And then Minogan or somebody else, I think Letikov was involved in that too. They changed the arrangement of the fields and maybe make some focused or something. And Ashkin would show that that didn't work. And finally, Ashkin and Gordon published a paper that became known as the optical Earnshaw theorem. And I'm going to just jump on to here. It was published in 1983, which was the year we were first doing those diffraction experiments. And the central idea is that if you have a scattering force that's proportional to the flux of photons, and you have no, in this region here, you have no source or sink for the photons. You just imagine the photons. Well, there may be more photons going in than out over here, but off to the sides, there are more going out. And effectively, that's what Ashkin's counterproofs of Minogan's schemes always boiled down to was you didn't think of this crazy off-axis direction, the 113 direction, but in that direction, look at this calculation. It shows that there's more light going out than coming in. So therefore, the scattering force can't be inwards everywhere, and you can't trap glass beads. That's what they were really talking about. So during a seminar at MIT, Alain Aspect mentioned the optical Earnshaw theorem, and afterwards, one of my students, Eric Rabb, said, "What was that?" And so, being in the role of a teacher, I started to give a very clear explanation. And I said, so assume that the cross-section here is constant. Well, wait a minute. That's true for glass beads, but it actually isn't true for light because the light can be polarized and the atom can be in one quantum state or another. So this whole proof is blown away. And we started thinking about, is there some way to, even in the regime of no saturation, is there some way to make a trap? And we started thinking about this sort of idea here. And this paper that we wrote with Carl Wyman and actually Vanderlees, a co-author, on which we imagined light coming in this way and focusing down light coming in this way and focusing down the other way. So you see on the sides here, both light beams are traveling in, so the force will be in. Now, over here, the outgoing beam is stronger, but maybe you can put something there like a magnetic field, or you can have some way to optically pump the atoms that will make them interact more strongly with the light going to the right here. They get to here, and there's more light going to the left and to the right, but the atoms are interacting much more strongly with the light going to the right, in which case they'll get pushed back. So that was our idea. And Stig Stenholm ran a conference in Helsinki. Well, it was up north of the Arctic Circle, but you had to go to Helsinki to get there. And then at the end of this talk, which Carl and I gave jointly, I challenged the audience to come up with ways to get around this optical Earnshaw theorem, because we'd been trying some at MIT and we hadn't gotten any to work. Or we were in that process, but I figured we needed more ideas at that point. And so at lunchtime, as we were getting our food, Jean Dalibard came up and he talked to me and he said, you know, I had an idea that I called optical ping pong. And it was that if I was way detuned from the resonance like this, but I had opposite traveling waves, but as the magnetic field, but there was a magnetic field gradient, when the atom got way over here, it could come into resonance with the right going beam, and over here it could come into resonance with the left going beam, and then it would get pushed back. So it would be optical, like optical ping pong. And it was an experimental failure. And in fact, he didn't even put it in his thesis. But I'm thinking about this scheme, and I told him why I didn't like the scheme. I said, I thought we would do better to try to keep making a trap that had a good polarization of the atoms. That would be ideal. And this scheme involved sigma plus coming one way and sigma minus the other. So the atom would get all messed up, and as it moved from side to side, it would change. It would get optically pumped. And I didn't want to talk about that. I didn't want that. I thought it was a bad idea. I didn't say it quite that strongly. I said, well, it was interesting. I liked the idea because it was symmetric, but I didn't like the idea because it didn't optically pump. Well, as we kept getting more failures, finally I said, look, thinking about this, I realized that if we made delta small, it would also become Doppler molasses. So it had the possibility to trap and to cool at the same time. So that looked good. And then what about the hyperfine structure? And so I told Eric, look, you've got to do a detailed calculation and figure out what'll happen with all the hyperfine and the optical pumping that was going to result. So he went off for a few days and started doing this calculation. Then he came back and he said, you know what? I realized that this actually doesn't have to be a one-dimensional trap. It'll be a three-dimensional trap, because if we start with these opposed windings here so that we get the one-dimension field along here, owing to the fact that it makes a spherical quadrupole field, we have the field going out in this direction here and out in the other direction to the other side. So it's just the same as coming in here, except we'd have to reverse the polarization. So we realized if we could put 6 beams on optical molasses and a little magnetic field, we would have a trap. So Steve Chu had been talking to us about collaboration, or to me about collaboration, saying, look, I got a good apparatus and you got lots of students. So we took this idea out of Bell Labs, and whammo, it worked the first time. And so that's the MOP, and that's in 1987. And it was really a huge breakthrough, and was a discovery. All of a sudden, with fairly quickly, it was shown by Carl Wyman. Well, we knew at the time we actually could just shut off the cooling beam, and the trap would still collect atoms out of the residual sodium in the vacuum. And then I think it was Carl showed that you could make this trap with cesium that would work. And so that was really a great discovery. And about that time, I made another great discovery. And he's pictured in this picture. I hope you can recognize Wolfgang Ketterle there and myself in the background. And what we set ourselves to think about was how could we get from optical pumping to evaporation, which we knew could work below, could work down to any frequency. And the basic problem in doing this, the idea is that you release the top, the hottest molecules escape from the force of the binding, the attractive forces between the water and the molecule, and they take more than their share of the thermal energy, and so the remainder of the atoms get colder. The trouble is that atomic cross sections are less than 10 to the 4 square angstroms, but the photon absorption cross section is greater than 10 to the 7th, and the light trap gets killed by the absorption of the atoms when you try to get the density up. So the absorption kills the trap long before the evaporation can begin. And so we started thinking of all kinds of optical pumping in dark states, and finally came up with a very, all trying to think, how can we increase the density to get to the place where we can do evaporation? And finally we just put a piece of black tape on the optics, and all of a sudden we got this dark spot. And what you see there looks pretty much the same, except it doesn't jump. It isn't quite so unstable. It doesn't jump around as much at high density. And then when it turns out you have 99% of the atoms are in the middle, but they're not, they're in the F equals 1 hyperfine state, so they don't scatter the predominant light around, which is F equals 2. So we made some absorption plots, and we showed that it had an optical density of 100. And wow, so then we were in business. And I have to skip over this. It's one of the elegant applications of the magneto-optic trap by Xiantan Liu, and ZT was doing all kinds of groundwater studies by using rare radioactive isotopes of krypton and argon. And krypton 85 gives you 10 years. Krypton 81 gives you sort of 500,000 years. And you can use these things to see how long it actually took water to get into your aquifer. I mean, it's just lovely work. And he looks at seawater intrusion, and you can sometimes show that some aquifers have 2 different sources. It's wonderful. Look, this all led to BEC, and I might just say one more thing about how people finally got to BEC. And this is, if you go back to evaporation, you have the problem that when your coffee is at 80 degrees centigrade, Celsius, 80 degrees Celsius, it cools off quite rapidly. But the evaporation will never cool it substantially below room temperature. So why won't it cool? What stops the cooling process is that the temperature gets so low that fewer and fewer atoms in the Boltzmann tail are energetic enough to escape. So the escape rate goes down, and the cooling rate goes to 0. And one night when Chris Helmerson and I were sitting, it was actually New Year's Eve. It was New Year's Day about 1 a.m. Chris and I had gone out to celebrate New Year's, and I had promised Arosh that I would get my ICAP proceedings in. And so we were writing up some of the last things, and we got about maybe 1 o'clock. We started thinking, hey, what if we put in RF? Wouldn't it be like a hole in the trap? And then we could move the RF, and we could lower it, and we could keep the evaporation rate constant, and this should just work. And pretty soon everybody showed that it did, including Wolfgang, shown here, he's made 2 BECs in 1995. The Gilla group of MIT alumni, Carl Wyman and Eric Eric Cornell in the other order. Eric Cornell and Carl Wyman, it was actually Eric's experiment. They made a BEC in July, I think it was. So Wolfgang was the second, and I wasn't collaborating with him anymore. I also want to just show you a dose of experimental reality. So let's see, I think I showed you that picture earlier of Wolfgang and myself in the lab in 83. And here's the lab in 2001. And the apparatus that we were leaning over is this well-hidden vacuum system inside. And now by 2003, it's gotten even more complicated. This is Aaron Leonhard, and this is Deep Gupta, and this is the tube for the lithium light coming in, and you can see that red light. I guess you can't see the sodium light, which is still on here. Anyway, so I think that I'll end my talk there. And I just want to say one thing, and I think that, this is a posed figure here because it's in the daytime when the photographer would come by. But those of you who are experimentalists know that when you have an apparatus that's as complicated as this, it takes most of the day before it goes at all. In fact, one of the wonderful pictures from Dan Stamper-Kern's thesis showed the hour of the day at which the figures in his thesis were taken. And as you see, there is virtually nothing in the morning. And then after lunch, after 12 p.m., it sort of ramps up. And then there's a drop here at 6 p.m., which is when people go to dinner. And then it gets better and better. And it stays pretty constant until like there's a big peak in here between about 8 p.m. And those of you who've been in the lab then know what it's like. Everyone else has left the building. The janitor's come and gone. The power is stable. The water temperature is stable. There aren't trucks rumbling by and making stray magnetic fields. The power is stable and your magnetic fields are stable. Everything starts to work. It starts to hum. And I've said to students, look, you don't go home until either the apparatus breaks down or you break down. So you'll see that this is where people really drop off, is after about 2 a.m. And then if you've been there, you know that really this experience of trying to predict something new and trying to find out where it is in parameter space and chase after it and go after it with a couple of other people in the lab. It's very, very human bonding experience. And I think it goes back to when we were hunter-gatherers. It's the experience of the hunt. You're off, there's a few people, and you're trying to get a valuable goal, and you have to think very hard about where it is and what kind of apparatus you're going to have to use to get where you want to be. And so with those thoughts, I will end my talk, and I'm happy to entertain any questions.
Well, thank you very much, David.
Okay, I think I stopped sharing.
And
the
we all
screen.
appreciate very much you still using the original pictures and the transparency from the old times, which is kind of very nice.
Well, yeah, Vanderlei, there's a certain art in those pictures.
Yeah.
That, the multicolored pens and everything. I think maybe Claude Cohn-Tanuji was one of the best practitioners of livening up a theoretical presentation with the colors. Yeah, you can do that now, but it's more work to do it in PowerPoint. Anyway, yes, so are there questions, I think is the thing.
Okay, so let's start by seeing if we have any questions here in the audience. Well, there is a couple of questions that came to me, David. So I'm gonna ask you here, people that ask from the YouTube and so on. The first question is, how comes that you never merge cold atoms with atomic interferometry?
Cold atoms, yeah, well, what happened was that when Wolfgang came to MIT as my postdoc and then transitioned to his being a faculty member, my department head was worried about Wolfgang getting tenure and the fact that my reputation at that point overshadowed his. And so I had to sign an agreement that I wouldn't collaborate with Wolfgang and until ultimately he got tenure. And then when, at that point, we decided that the sensible thing to do was to start doing atom optics and atom interferometers with BECs in his apparatus. So we started up a collaboration with some joint students, and we did that for a while. But I think, I think what I should have done was I should have shifted to doing atom optics with atoms from a MOT and worried about transferring them to a magnetic trap and just cooling them off by adiabatic expansion. I think that would have been a good route to go, but we were making hay with that old atomic beam in the atom optics business, and so I just kept doing that.
Okay. Another question is, if one start experiments with matter waves interferometry today, what would be a nice problem to get involved with?
Well, first of all, I have to plead not quite ignorance, but being 20 years behind the times, because that's how long I've been doing education, and ignoring the literature. I was kind of a guest of honor at an atom interferometry conference a few years ago, and I foolishly agreed to talk a little about the history, and I couldn't resist making some predictions about things that I thought would be good, like precision measurements of gravity, measurements of the gravitational constant, more atomic physics. Well, I don't remember all the things, but much to my embarrassment, as the conference went on, I realized that most of these ideas had been done at least by one other person who was talking at the conference already. So I would recommend that you go to a conference or review articles about atom interferometers and figure out what's interesting there. But I had always thought that they were great, especially slow atom interferometers were great for measuring acceleration and measuring gravity and like inertial navigation. There was a big program funded by the military to do precision inertial navigation, to use the atoms as rotation centers where we were a pioneer, and as gravity sensors where the Stanford guys were pioneers. And Mark Kasevich is an absolutely fantastic engineer, and he started making atom interferometers with slow atoms or with trapped atoms that were really getting to the point where you might conceivably make a box, a sort of meter-sized box, and put it in the back of a Jeep and drive around for an hour, and without any reference to anything outside, like the GPS or any landmarks, you could navigate and know where you were to within 10 meters. That's the kind of precision that's coming along. And that kind of precision, if you launch atom interferometers into space, you can make gravity wave detectors that detect very low frequency. People have been talking about doing that. But I'm really, I don't think I'm the person to listen to about that.
Okay. Well, there was a question here about if the interferometer could measure the, could be used as a gravimeter, and you already said yes, and of course. But now I'm going to complement the question is, we know that the big G on gravitational theory is a constant that's very badly measured. Do you think that with atomic interferometer we could improve that and maybe discover something new that's missing on this gravity stuff?
Okay, that's always intrigued me too, is that constant, there's, the big G's been a lot of controversy, and I don't even think it's known to a part in 10 to the fifth, whereas most other fundamental constants are known at the part in 10 to the ninth or so level. Part in 10 to the eighth anyway. So what's really interesting is that when you measure the little g or the acceleration with an atom interferometer, you're really checking the equivalence principle, and that seems to work just fine. If you want to really measure big G, you want to measure the phase shift due to the gravitational interaction. And so what you might do is have two packs of atoms that get widely separated and then come back together and measure the fringes, and then widely separate them again. But the second time, wrap your lead cylinder around them so that these atoms are in the gravitational potential, and you have to do it fast. You have to do it like the Aharonov-Bohm effect, where if you do it slowly, there's a force on the atoms as they go in. You don't want to use the equivalence between the gravitational interaction. You want to just wait until the atoms are here, and then you want to clap your lead cylinder around it and make a gravitational interaction, and then pull it apart and let them fall back down again and interfere. And I believe that some people have begun to see an effect this way. And I don't remember, I don't read, there's about 100 times more educational literature than there is AMO literature, and I can't keep up with that at all in my education research. So I don't read the AMO literature at all anymore. But I did happen to see this one article. I don't remember if it was the guys in Europe or Kasovich's group at Stanford, where they have 10-meter high interferometers, and the atoms are well separated in the course of that. And so then they can just barely begin to see the effects of big G. So they'll have to improve that apparatus by 5 orders of magnitude. I think the best way to do that would probably be to do it in space, but probably as its own space station, because otherwise it would be sensitive to the gravitational gradients due to the other members of the space station.
Wow, okay.
So that's my answer. Not right away, but hey, it's a wonderful thing to do. And it's interesting to see that the gravitational interaction would in fact simply add a potential in to the phase that you would detect with an atom interferometer.
Okay, if there is no further questions, we would like to thank David again for the nice talk, give us an overview of how the things was built up and what that everything turns into this big success of the cold atoms. So thank you very much, David. Don't forget, you have to give us a talk on the 25th of March, and we're going to send you all the information and everything. So thank you very much once more.
Don't forget, Vanderlei, that it's a talk in which I am up to date. And it's the title is something like Academic Dishonesty in the Age of the Internet.
Okay, well.
Like people cheating online is basically what it comes down to.
Oh, that's perfect. So thank you very much. Have a good day, David. Thank you for giving your time to us in the School of Quantum Fluids. Thank you very much. Let's give another thank to Dave. Okay, so